Hello, and welcome to our calculation of a very explicit Fourier series. We'll take f of x equals x and an arbitrary period p greater than 0, and we want to find the real and complex Fourier series for f on the interval minus p to p. So, let's do the real Fourier series first. We need to evaluate our AK coefficients. So the AK coefficient on f is 1 over p, integral minus p to p of x, cosine of k pi x over p for any k greater than or equal to 0. And we'll need to evaluate the bk coefficients, which will be 1 over p times integral minus p to p x, sine of k pi x over p. Here k is greater than or equal to 1 for the bk's. So the natural thing to do is just to try to get these antiderivatives. First, we'll integrate by parts. So if you do that for x cosine of k pi x over p, you get back the lengthy expression, and read it with me carefully, p squared divided by k squared pi squared times cosine of k pi x over p plus k pi x over p on the outside times sine of k pi x over p. And so this immediately is a warning for us. If I were not to really care what k is, I would get a k in the denominator, and that tells me this isn't going to work for k equals 0. I'll have to do the k equals 0 case separately. And that will happen rather frequently in the examples that we do. I think it's just a consequence of the way integration by parts works, which is the way we often evaluate these antiderivatives. By the way, if we were in class at a blackboard together, I would not be carrying out the integration by parts here. And on homeworks or practice problems, I'll either try to make the integrals easy for you, or I will say use a computer algebra system like MATLAB or Maple. You don't want to get bogged down too much in integrating by parts and doing other antiderivatives here. And when it comes time for an exam, I'll either give you a really easy integral or I'll tell you straight up what the antiderivative is. We should not be worrying too much about our calculus at this point in life. So let's just do the k not equal to 0 case first, since we have this big mess of an antiderivative to play with. I want to calculate ak of f is 1 over p integral minus p to p x cosine of k pi x over p. And so that is 1 over p times my antiderivative, p squared over k squared pi squared, times the stuff in brackets. I'm not going to read what that stuff is. Evaluated at x equals p, and then subtract off evaluating that at x equals minus p. So let's plug in x equals p and minus p and do the actual subtraction. Oh, I have a 1 over p and a p squared multiplied together, so I'm going to lose a power of p. So here's what I get. p over k squared pi squared times this large expression. Cosine of k pi plus k pi sine of k pi minus the large expression cosine of minus k pi plus minus k pi times sine of minus k pi. So basically x's get replaced by p's or minus p's, and either k pi's or minus k pi's result. Now here I need a couple of trig facts, and these are absolutely essential for you to know for any kind of Fourier series calculation. You can always recover them by thinking about the unit circle and drawing and doing some scratch work, but I would encourage you to commit these to memory. First of all, sine of k pi is equal to 0 for all integers k, and cosine of k pi is equal to minus 1 to the k for all integers k. So let's think about jumping around the unit circle in steps of pi each time, and you'll get these. So what does this tell us? Well, ak on f, that Fourier coefficient, is going to be p over k squared pi squared. The cosine of k pi becomes a minus 1 to the k. That first sine of k pi is 0. Then after the subtraction, I have cosine of minus k pi is still minus 1 to the k, so I have a minus 1 to the k, and then that sine of k pi factor goes away. So I have minus 1 to the k minus 1 to the k, and that is equal to 0. So ak on f is equal to 0. Here's another way I might have seen that without doing the antiderivative, but maybe this isn't obvious at first. ak on f is 1 over p integral from minus p to p x cosine of k pi x over p. This is a symmetric interval going from minus p to positive p. The function x is odd. The function cosine of k pi x over p is even. So the integrand, the product, x cosine of k pi x over p, is odd. The integral of an odd function over a symmetric interval minus p to p is always 0. This is a good way to check your work by seeing a different property of the integral. And you're welcome to use these tricks for evaluating integrals and not actually do antiderivatives whenever those tricks apply. Let's also do the k equals 0 case now and round out all of our ak coefficients. Well, for k equals 0, I have a0 on f is the integral from minus p to p of just plain old x dx times 1 over p. And again, that's equal to 0. Either I do the antiderivative x squared over 2, or I use the fact that I'm working with a symmetric interval minus p to p, and my integrand x is odd. So ak on f is equal to 0 for all k. And that we'll see later on is a general property of all odd functions over symmetric intervals, that their Fourier coefficients there are always 0. Now we'll compute the bk coefficients. Bk on f is 1 over p, integral from minus p to p of x sine of k pi x over p. And here I'm working with k greater than or equal to 1, so I have no, in theory, division by 0 issues to worry about. So again, I integrate by parts. The integral of x sine of k pi x over p is going to be p squared over k squared pi squared times the quantity sine of k pi x over p minus k pi x over p cosine of k pi x over p. Looks similar to what we had when we had the cosine instead of a sine in the integrand, but still a little different. And again, I think I used Maple to do this. Do the integral however you find easiest. So now my bk coefficient is going to be 1 over p times p squared over k pi squared times this large expression in brackets evaluated at x equals p, and then subtract off from that the evaluation at x equals minus p. And so outside the brackets, I lose a power of p from division. And then inside the brackets, I replace all my x's with p's, and then all my x's with minus p's. And so I get sine of k pi minus k pi cosine of k pi minus the quantity sine of minus k pi minus k pi times cosine of k pi. So now I have to see all my sines go away. So sine of k pi is equal to 0, sine of minus k pi is equal to 0, and my cosine of k pi's turn into minus 1 to the k's. So I'm left with p over k squared pi squared times minus k pi times minus 1 to the k minus k pi times minus 1 to the k. Okay, and that turns out to be equal to minus 1 to the k plus 1 times 2p over k pi. Let's check my claim there a little bit. Both terms inside the brackets had a factor of k pi on them, so I lose a k pi from the denominator. Each term has a minus 1 to the k in it, and an extra factor of a minus on it. So that's my minus 1 to the k plus 1. I retain a p, and then I get a factor of 2 because both terms are the same. So bk on f is minus 1 to the k plus 1 times 2p over k pi. So the formal real Fourier series of f of x equals x on the interval from minus p to p, of course, is the sum from k equals 0 to infinity of ak on f cosine of k pi x over p plus bk of f sine of k pi x over p. And here my ak's all dropped out, including the k equals 0 term, so I'm left with just the bk terms. This is the sum from k equals 1 to infinity of minus 1 to the k plus 1, 2p over k pi, sine of k pi x over p. And if you want, you can factor this nicely as 2p over pi times sum from k equals 1 to infinity, minus 1 to the k plus 1 over k, sine of k pi x over p. Now for the complex series, we could use one of our lemmas, I think it's lemma 2.4.2, that tell us what the complex Fourier coefficients are in terms of the real coefficients. But because this is an introductory exercise, let's actually do it directly and assume we didn't spend all this time calculating the real Fourier coefficients, and we'll just get the complex Fourier coefficients from scratch. So we want to calculate f hat of k is 1 over 2p times the integral from minus p to p of x times e to the minus ik pi x over p. And we'll integrate by parts to get this antiderivative. Specifically, I'd take u equals x and dv equals e to the minus ik pi x over p dx. And I'm saying this in a little more detail here because even though I have this factor of I in the exponent, the square root of minus 1, I can still do all my usual calculus manipulations, integration by parts, u substitutions, just treating I as a plain old constant. And in the notes, I direct you a little bit to where you might see that in the appendices if you want to review doing calculus with complex valued functions of a real variable. So I integrate by parts as I usually do, and the indefinite integral of x times e to the minus ik pi x over p is the quantity p times ik pi x plus p times e to the minus ik pi x over p divided by k squared times pi squared. So if I hadn't been paying attention, this immediately tells me that this antiderivative is only valid for k not equal to 0, because otherwise I'm dividing by 0 squared. So for k not equal to 0, we'll deal with k equal to 0 in a moment, I have f hat of k is my factor 1 over 2p times this antiderivative evaluated at x equals p, and subtract from that the antiderivative evaluated at x equals minus p. And so I plug in x equals plus or minus p, and I get, let's see, well, I have a factor of p in the denominator and p in the numerator, so the p's go away. I pull out my factor of 2 in the denominator, my factor of k squared pi squared in the denominator, and then I have the subtraction p ik p plus p times e to the minus ik pi minus ik pi p plus p times e to the ik pi. So if you're copying this out by hand, definitely hit the pause button for a moment and make sure you have all your p's and k's, or p's and q's, whatever it is, in the right place. So let's try to simplify this a little bit. What is e to the ik pi? Well, from Euler's formula, that's cosine of k pi plus I times sine of k pi. So our sine of k pi goes away, and we're left with e to the ik pi equals minus 1 to the k. So now f hat of k, let's see, my e to the minus ik pi becomes a minus 1 to the k. My e to the ik pi becomes a minus 1 to the k. I look inside my big parentheses here on this second line of f hat above, and I see every single term has a p in it. A p, and then in the minus term, another p, a p. So I'm going to factor out this p and divide that by 2k squared pi squared. And so I'm left with doing the arithmetic on ik pi plus 1 times minus 1 to the k minus ik pi plus 1 times minus 1 to the k. And I factor out my minus 1 to the k. So now f hat of k is p over 2k squared pi squared times minus 1 to the k, then times the quantity ik pi plus 1 minus ik pi minus 1. So the plus 1 and the minus 1 go away, and I'm left with my Fourier coefficient f hat of k equaling p over 2k squared pi squared times minus 1 to the k times 2ik pi. And here again, you might want to hit your pause button and check the arithmetic there. Okay, so you're back to me live, and we see I have a k pi in the numerator and a k squared pi squared in the denominator, so I'll cancel those out, and I'll write f hat of k at last as ip over k pi times minus 1 to the k. And this will all presume that k was not equal to 0, which of course we can see because we're dividing by k. So for k equal to 0, we have f hat of 0 is once again 1 over 2p times minus p to p of x dx, and that is equal to 0. So the formal complex Fourier series of f of x equals x on the interval minus p to p is the sum from k equals minus infinity to infinity of f hat of k e to the ik pi x over p. So that'll be the sum from k equals minus infinity to infinity, and here I've put a subscript there. I'm saying now k is not equal to 0 of ip over k pi times minus 1 to the k e to the ik pi x over p. And that is, if you want to factor a little, ip over pi times the sum from k equals minus infinity to infinity, k not equal to 0, of minus 1 to the k over k, e to the ik, pi x over p. That was quite a bit of work for a very simple function, f of x equals x. And last, let me comment on why I have these adjectives formal series here. When we're talking about a formal series, a formal trig series, a formal power series, it basically means we're just doing the symbol pushing we just did. We're not worrying at all about whether or not the series converges for a given x. We just want to know what is the formula for the series. And here we have it.